For decades, our entire digital world has been built on the back of rigid, brittle silicon. And it's powerful, sure. But if you want to build the next generation of wearable tech, or say wrap a continuous display around a robotic joint, or even create highly sensitive artificial skin, well, silicon is fundamentally limited. You literally can't bend a traditional motherboard around your wrist without snapping it in half. So in this explainer, we're diving deep into the cutting-edge chemistry that totally bypasses these physical limits, and we'll see how flexible processors and advanced low-power memory are actually becoming a reality.
To really get this paradigm shift, we have to look at the fundamental difference between traditional silicon MOSFETs and carbon-based organic materials like Pentacene. Think of a standard silicon chip kind of like a superhighway. The silicon atoms are locked into this massive, rigid, three-dimensional crystal lattice. The electrons, they just flow freely down continuous energy bands, exactly like cars on that open highway. It's incredibly fast, but if you bend the silicon, that crystal lattice snaps, and boom, the highway is destroyed. Now, organic materials operate completely differently. Instead of a massive continuous crystal, they're made of discrete individual molecules just loosely packed together. And because they aren't rigidly locked into some monolithic structure, the whole material can bend and flex. The electrical charge doesn't drive down a continuous highway. Instead, it moves via this process called molecular hopping. It literally jumps from one discrete molecule to the next. The material can flex. Those little molecular stepping stones might shift slightly, but the charge just keeps on hopping. That is exactly what allows the processor to function, even when it's bent in half. Plus, since we aren't trying to forge a perfect crystal, we can process these organics at much, much lower temperatures. A real game changer.
To map out this transition, we've broken this explainer into 5 logical chapters. We'll start with rigid versus flexible electronics, move inside organic semiconductors, see exactly how Pentacene devices work, explore next-gen ReRAM memory, and wrap up with TiO₂ and sol-gel synthesis.
All right, let's jump straight into Section 1, Rigid versus Flexible Electronics, the Paradigm Shift.
The entire foundation of this shift lies in organic semiconductors. Now, unlike the metal and silicon you might be used to, these are entirely carbon-based materials, and they conduct electricity through their conjugated pi electron systems. To understand how they actually work without those continuous silicon energy bands we just talked about, imagine a ladder. Organic molecules rely on specific, discrete energy levels. The highest occupied molecular orbital, or HOMO for short, is basically like the highest rung on the ladder that currently has people, or in this case electrons, standing on it. The lowest unoccupied molecular orbital, the LUMO, is just the empty rung right above it. To move an electrical charge, electrons need a very specific amount of energy to jump up to that empty LUMO rung. Or alternatively, holes, which are basically just positive empty spaces, can move right along the occupied HOMO rungs. By carefully overlapping these rungs between neighboring molecules, engineers can create a highly controlled path for electricity that stays entirely physically pliable.
Moving right along to Section 2, Inside Organic Semiconductors, meet Pentacene.
Take a look at this planar, 5-ring structure. This specific molecule, Pentacene, is literally the absolute star of the flexible revolution. It's got the chemical formula C22H14, and those 5 linearly fused benzene rings create a beautifully extended pi-conjugated system. Essentially, what that means is there's a massive cloud of shared electrons spread across the whole flat molecule. This structure is perfectly tuned for that molecular hopping we discussed earlier. Because of its specific HOMO energy level, it's actually very easy to inject positive charges, those holes, from metal electrodes directly into the material. This makes Pentacene an incredibly efficient P-type organic semiconductor, totally laying the groundwork for our flexible circuits.
And here's where it gets absolutely fascinating. By simply tweaking the chemistry just a bit, we can entirely reverse the material's function. If we take that exact Pentacene molecule and replace all 14 of its hydrogen atoms with highly electronegative fluorine atoms, we get perfluoropentacene. Fluorine acts kind of like a vacuum, strongly withdrawing electron density right from the center of the molecule. This significantly lowers the LUMO energy level. And just like that, you flip the molecule's behavior. It transforms from a P-type material that transports holes via the HOMO directly into a highly stable N-type material that transports electrons via the LUMO. It's just a perfect example of how electrical behavior in these advanced systems is strictly governed by custom electrical architecture.
Okay, so we understand the molecule. Let's hit Section 3, how Pentacene devices work.
So how do we actually translate those molecules into a working piece of hardware? Well, we build a flexible sandwich, layer by layer. Down at the base, we use a flexible glass or plastic substrate. Then we lay down tantalum for the gate electrode, mostly because it's a superb conductor and inherently resists oxidation. On top of that sits our absolutely crucial dielectric insulating layer, tantalum pentoxide.
This specific insulator is chosen because it has a really high dielectric constant, meaning it can hold a strong electric field without letting current leak through. And critically, it can be deposited at room temperature. That completely bypasses the need for multi-billion-dollar ultra-hot foundries. Sitting right on top of that insulator is our active Pentacene layer, which is finely capped off with gold source and drain electrodes. The whole shebang.
Let's look at exactly how this construction operates in real time. When we apply a voltage to that tantalum gate, an electric field projects upward, passing right through the tantalum pentoxide insulator. This field acts kind of like a magnet, pulling positive holes within the Pentacene layer down to the boundary where those two materials meet. These gathered holes form a temporary conductive channel, bridging the gap between the gold source and drain. When a separate voltage is applied across those gold contacts, the holes begin to move. Now, as we established earlier, they don't flow in a continuous stream like they do in a rigid MOSFET. Rather, the current hops across the conjugated molecules like stepping stones in a river. That molecular hopping represents our transistors switching on, literally processing data right on a substrate that could be bending around your wrist at that exact moment.
A processor definitely needs memory, so let's transition to Section 4, Next-Gen Memory, ReRAM.
A flexible processor is pretty much useless without memory to store its calculations, right? And if we're building wearable tech or smart skin, that memory needs to consume virtually zero power when it's just sitting idle. Enter ReRAM, or Resistive Random Access Memory. Instead of trapping a volatile electrical charge to store data, like an old flash drive, ReRAM does something incredibly clever. It physically alters its own internal resistance to remember information. It is a strictly non-volatile technology. What that means is, once you trigger a change in its resistance state, it locks into place and retains that memory indefinitely, even when the power is completely disconnected. No power, no problem.
The way it achieves these states is so cool. When you pass a specific electric field through the memory layer, oxygen ions are literally pushed out of their normal spots in the material's structural lattice. Think of cars backing out of a crowded parking lot and driving away. They leave behind empty spaces, which we call oxygen vacancies. Because of the physics at play here, these empty vacancies actually link up, forming a microscopic physical wire, a conductive filament, that bridges the gap between the electrodes. Electricity flows beautifully down this filament, dropping the device into a low-resistance state, which gives us our logic 1. But if you reverse the voltage, the oxygen ions are pushed right back into those empty spots. The filament ruptures, breaking the wire, and the device jumps back to a high-resistance state, giving us our logic 0.
To understand exactly how we make those resistive filaments, let's move to our final section, Section 5, TiO₂ and sol-gel synthesis.
To house those conductive filaments, titanium dioxide, or Ti2, is widely considered the absolute perfect nanomaterial. Why? Well, it's incredibly stable thermally, meaning it won't just degrade under continuous use. And structurally, it is exceptionally prone to forming those crucial oxygen vacancies we need to build the filaments. Furthermore, Ti2 acts as an excellent hole-blocking layer in these circuits. You can think of it like a strict microscopic traffic cop. It ensures that only the right type of charge passes through the device and actively blocks the wrong type from leaking out. This is absolutely crucial because it prevents the memory cell from accidentally draining your wearable device's battery while it's just sitting idle.
But the real game changer here is how we actually manufacture these TiO₂ nanoparticles. Traditional silicon manufacturing requires massive vacuum chambers and extreme heat. But by using a wet chemical method called the sol-gel process, we can essentially brew advanced nanomaterials right in a standard chemistry lab. This process totally democratizes high-tech manufacturing, allowing engineers to precisely control the structure and purity of the memory materials starting entirely from room-temperature liquid precursors. The underlying chemistry of this sol-gel process is surprisingly elegant. First, we take a liquid titanium precursor dissolved in a solvent and slowly add water. This triggers hydrolysis, breaking down the precursor and forming hydroxide groups. Next comes condensation, and you can visualize this almost like making jello. The isolated molecules start linking arms, undergoing a chemical condensation reaction to form an interconnected, three-dimensional TOTI network. You can literally watch the loose liquids thicken into a structural gel. It's wild! Finally, we move to calcination. We dry out the remaining solvents and bake the gel down. What's left behind is a highly ordered, pure, crystalline titanium dioxide matrix perfectly tuned to hold oxygen vacancies for our ReRAM chips.
So we've seen how organic Pentacene provides mechanical flexibility through molecular hopping, and how inorganic nanomaterials like TiO₂ provide defect-driven memory storage that requires virtually zero idle power. As we wrap up this explainer, I want you to consider this.
How soon will we fully integrate these exact organic and inorganic technologies to create synthetic skin for prosthetics or robotics? Skin that not only senses a touch using flexible Pentacene, but instantly stores the memory of that physical interaction locally within its own TiO₂ layers right at the point of contact. The chemistry is already here. The next step is applying it.